Jean-Marc Chaumas just said earlier in the afternoon that he hates vulgarization of science. I must say to start with that I'm not really fond of this kind of conferences, for a reason you will understand later, I hope. Unlike my scientific colleagues here, I've never been personally involved in any collaboration with an artist, I mean, apart from myself. The reason why I've been, I think, co-opted here is because of my work on sprays, the fragmentation of water, and this is what we will talk about. So that's the topic. This is a spray. This is a set of droplets, as you can see. And the interest for us scientists is to understand this kind of object. And again, making reference to the excellent presentation by Jean-Marc, the pictures I am using here, pictures I will be displaying, are for us data from which we extract information, which are further processed, and which we use to give an overall representation of the phenomena we like to talk about. They are not primarily aesthetically oriented, let's say. It may happen that they are nice, that they are pretty, that they are ugly, but the bottom line for us is that we want to extract information. All right, so for instance, this picture is a picture which has been used to compute an object which is called an histogram of droplet sizes. Indeed, as you can see, there are in the same spray the coexistence of big droplets, average size droplets, small droplets, and this is what interests us for many applications, but also as a subject of basic science. All right, so let's accumulate a number of examples. I will mostly be showing pictures, accumulating examples, and then we'll have a more, let's say, organized discussion afterwards. So one of the first experiments we did with sprays was it's closely related to the very nice movies the previous speaker has shown of breaking waves and what happens at the crest of the waves when wind blows over the sea surface. When there is this fast gaseous stream of air which blows at the surface of the sea, the phenomena involved there are very well represented by what we see here. It's a jet of liquid that you see, and what you don't see, but what you can guess that exists, is a coaxial airstream which is destabilizing this jet, which would otherwise remain smooth and circular. So the surface is destabilized, creating waves, as the one we've seen, and at the crest of the waves, you may notice the existence of these elongated structures which are stretched in the wind, very similarly to what we've seen before, and which are the objects which produce the spray, the droplets we have on the beach. So we're interested in all this, and the figure and the formula below are attempts to collect the data from these movies or from these pictures and to construct the histogram of the sizes. So what is interesting in that process and what interests us is that a single process produces a wealth of different sizes. Diversity is naturally involved, is naturally created by this kind of processes. And yes, the objects which are responsible for this diversity are those you were seeing before, and I'm showing one isolated one, which in the course of its fate in the airstream has been stretched and breaks into a collection of droplets which, as you can see, have very different sizes. So this is what interests us. this is what we call liquid ligaments, and as you will see, we will have these objects all along in my presentation and the different examples I will consider. So this is the pretty much the simplest realization of the cup of coffee which falls on the ground. You have all noticed that the liquid was spread out everywhere in the kitchen when you do a mistake, and this is the reason why. Maybe I can replay the movie, or no, I cannot replay the movie. So you see still pictures from the movie. You have a liquid which is immersed into a test tube. The important thing is that the interface of the liquid is curved. It is an hemisphere, and when the cup of coffee or the test tube rebounds on the floor, the interface of the liquid violently reverses, producing a concentrated jet, which in the end breaks into droplets. The same kind of thing can be made if the cavity is formed by a bubble immersed in the liquid. And as you can see, just after the shock, a very violent jet is expelled from the liquid surface, this jet being naturally unstable, producing this ligament with droplets. So that's an example of not water in the air, but air into water, which produces this cavity, which is interesting and which produces the interesting phenomenon itself responsible for the formation of the droplets. So that's an example, a very similar example. The process you've just seen using a test tube is essentially the one which is at play in your inkjet printer. Essentially, this is the phenomena they are using. They're deforming extremely violently a small cavity where the ink is, and the surface of this cavity is slightly curved so that a jet is violently ejected. And all the bottom line of the present day research in inkjet printing, let's say, is to remove these secondary smaller droplets at the skirt of the primary big ones, because these secondary droplets are annoying. They're making the print fuzzy. The idea of the engineers working on this kind of subject is that we should have more basic research to remove this kind of objects. So this is interesting. So these are Savart sheets to which it has been alluded to already this morning. There are objects which have been conceived during the 19th century by somebody called Félix Savart, with the idea of studying the phenomena of cohesion of liquids in the present case, but also cohesion in general. And the idea was to have a directed jet of liquid which, impacting on a solid surface, would be directed in all the directions in a more or less isotropic manner, and thus by forcing the divergence of the trajectories, one could gain insight into what causes the cohesion of liquids. So this is not only an object for the tourists on the highways. This is also an object of current research in order to understand how droplets form at the edge of these sheets. And yes, depending on the regimes, and essentially depending on the velocity of the jet when it impacts the solid surface, the sheet might expand in the air as a smooth object. This is the first picture on the top. But below, you see that some wiggles develop on the sheet, which is flapping like a flag would do. And this is the result of the interaction of this very thin liquid sheet with the environment, with the air, which, like a flag, promotes the oscillation of the sheet itself. And of course, the existence of these phenomena influence the way the spray is formed. Yeah, that's essentially also the process which is at play in the bursting of soap films. So if you burst the soap film which you have stretched on the frame, for instance, it would be the same with the bubble. And if you look carefully at the edge of this opening hole, you see that there is a characteristic flapping motion, which is the result of the interaction of the heavy liquid, the receding, fast, heavy liquid, with the light surrounding environment. The same phenomenon seen from the side. We have seen this picture earlier this morning, but it was a still picture. I'm providing the whole movie here. All right. Many different phenomena might occur. These transverse structures are also an object of very detailed research, and we are looking at the edge of such a flapping sheet here, and as you can see, the droplets form at the extremity of these singularities which have folded the liquid sheet. All right, let's continue in our catalog of ligaments and the way they are produced in the laboratory or in the industrial practice. There is a process which is called effervescent atomization. Effervescent, why? Because some holes are introduced into a sheet. So what we see here is a liquid sheet, very similar to the one you're making when you put some water in your garden. It's a stream of water which is forced to go through a tiny slit, thus producing a kind of a fan-like sheet. And if some, let's say, precursors are introduced in the sheet, nucleation might occur, producing these opening holes. At the rim of the opening holes collects the liquid, and the liquid produces these ligaments, which at the end will produce the droplets. The same if a liquid film is violently accelerated perpendicular to its plane. In that case, there is an instability which produces a set of holes, opening, collecting the liquid, and bursting in the end. Yeah. I have a movie showing this. You have not seen anything, so I'm replaying the movie. Okay, so this is the we are looking at a very tiny liquid sheet. It's 100 microns thick. It is accelerated towards us. We're making a movie of the film facing it. Some holes appear. They continue growing, they collect the liquid, and as you can see, the ligaments forming the web of liquid, having collected all the liquid constitutive of the film, finally break into droplets. So again, there is the formation of those ligaments. Same kind of process. There is a relationship between science and arts. You may also know that there is a relationship with science and technology. This is an industrial process producing, let's say, patterns very similar to those we have seen this morning, again in the afternoon in the highway thing. Again, we have a liquid sheet. This is a liquid metal liquid sheet. The process is called the grand shot process. It is used to form liquid pellets, which will afterward fall into a bath of liquid, forming solid pellets of metals. And the process it's $1 million process. This does not imply that it's an interesting one, but this is something which is going on at heavy loading every day to form these liquid pellets. And again, this is an object which is currently an object of research. You see the dynamics of the opening of the holes we have seen before, the formation of a ligament, and then the drop size distribution associated to it. Yeah, this is what occurs in real time when you seed a liquid sheet with precursors or nucleation sites, the holes form, collect the liquid, and then break as a jet would do. All right. I don't need to introduce what happens in the surf zone, because again we have seen a very nice movie of what happens when waves break on the beach, producing this foam. This foam is in fact a set of bubbles, so air into water. When the bubbles reach the surface, they stay there for a couple of, for a given time, for a certain time, and then they break and they pop up. How? Well, like this. This is a bubble reaching the interface, so we are sitting on a pool of liquid here, and after some time the bubble breaks, nucleating a hole, which forms, as you've seen, ligaments and then droplets. So again, there is a hole forming, a destabilization of the edge of the opening hole, and again the formation of ligamentary structures which produce drops. Okay, this is how aerosols are produced at the surface of the sea. Those are involved in the air-sea exchanges, and particularly in the air-sea balance of water vapor, of course. This process is dominant as soon as there is a little bit of wind. By looking at the same phenomenon in a different way, with a different kind of light, one sees that the bubble cup is not a static object at all, that there is some light, some life on it. There is a whole set of moving structures, and in fact, the moving structures you have on this very tiny shell are those which are responsible for the hole opening, which will decide of the death of the bubble. So it's quite interesting. And then, yes, the resulting aerosols again are produced by these breaking ligaments, which produce always this kind of distribution we have. I've not shown much formula, but you need to understand, I'm talking to the artist, that this is our language, and that there is an intrinsic beauty to equations as well. For instance, this is an equation which is quite nice. It expresses something which is interesting. I will not go into details. I just want to underline that the histogram of droplet sizes which are recorded at the surface of the ocean are fully understood in terms of the detailed mechanism I have just shown at the scale of a single bubble. So if you understand the product of a bubble bursting in the laboratory, you are able to infer what will happen at the scale of the ocean, and this is what this figure demonstrates. Yeah, I try a tribute to Etienne Jules Marais, the great precursor of, at least the French precursor of the high-speed movies. So this is a soap bubble constitutive of a liquid which is much more viscous than the one we've been using to study aerosols. We can tell because the ligaments produced by the opening of the hole are extremely elongated before breaking. They produce very tiny threads. But that was the first time that the process had been imaged. All right, let's go on with new examples. This is a process which I call the soft impact of drops, by opposition of the hard impact, which we will see in a minute. So the soft impact of drop is what? It's simply a drop of liquid which falls by its own weight in a gaseous stream. At some point, the resistance forces of the air are strong enough to deform the liquid to overcome the surface tension of the liquid the previous speaker was referring to. The surface tension, cohesion is involved in this process, but precisely it is not strong enough at this point to overcome the drag, the air drag imposed by the relative motion of the drop itself in its falling motion. And as you can see, it has undergone a transition from a spherical droplet to an inflating bag, bursting itself and producing a whole collection of sizes, of drop sizes. And we've been arguing that this process is related to rainfall, and precisely the kind of droplets we have on our windshield at the ground level. So this is, some colleagues have made these experiments again. Maybe it's quite interesting because the pictures are quite nice. The whole series of events is recalled here. We have, like in the previous examples, the formation of a ligament, of a liquid ligament collecting all the liquid which was initially confined in a spherical droplet. This time this ligament is a toroidal ligament, and its breakup produces a wealth of a broad range of sizes. And that particular process, when analyzed in a specific way, finally allowed us to understand and justify a long-standing question in the field of atmospheric sciences and meteorology, which is the spectrum, the histogram of the drop sizes one has at the ground level. So the data were known for a long time. The fact that in a single rain we have the coexistence at the ground level of big droplets, average size droplets, and small droplets was known for a long time. It was known since Wilson-Bentley, 1904. Using extremely clever experiments, he had no fast camera at that time, so he was obliged to be clever as opposed to us. He had already noticed that in a single rain you had all the sizes, nearly all the sizes. This kind of study has been a mechanistic interpretation of this known fact for a long time. So Wilson-Bentley, you may know it through his work. He was a farmer from Vermont, a place where snows falls quite some time. And he was fascinated by anything falling from the sky. He would have been topical for this conference, and he's essentially known for his work on snowflakes. He was called the Snowflake Man by Duncan Blanchard. Well, again, the phenomenology is always the same. We have colliding jets. We see them from not from the side but from the face. The collision produces a kind of a bay-leaf shape. Again, we have the formation of a ligament bordering, a rim bordering the bay-leaf, from which ligaments are stretched, which break and produce the droplets. One can see the fate of a protrusion form close to the impingement region, which degenerates into a stretched ligament and then produces drops. All right, we've seen the soft impact. This is for the hard impact, more traditional, the droplet impacting on a solid surface. There is again a quite large body of fluid mechanics explaining all this, but the phenomenology is the same, the formation of elongated structures which by their breakup form the ultimate spray. And this again is a phenomenology which has been known at least since Leonardo da Vinci. This is in the margin of book 3 of the Codex Leicester. You've seen a picture of it earlier this afternoon, the vortici. And it's always a subject of amazement. This is Irene Müller, is a photographer of all sorts of impact and fluid mechanics. She's an artist. Phenomena related to fluid mechanics in general. And so this is a subject which is still a subject of amazement through the communities. All right, so I have somehow finished with the zoo of phenomena. You've seen in the process of the formation of droplets, the predominance, if not the mandatory existence of elongated structures, which by their dynamics produce sizes which are by definition, and which are, because this is intrinsic to the dynamics, different from each other. Arts and science, because we've been asked to address this connection. And we've been, what? Yes, we've been asked. And we have also been asked to speak about ourselves, if I remember well, our personal experience. Right? So I'm taking advantage of this extraordinarily nice painting by Paul Signac called Le Nuage Rose. Paul Signac is the, as you know, a neo-impressionist, the discoverer of Saint-Tropez. And this picture, which I cherish the most in his, among his masterpieces, I have always in mind when I work in the lab, because I'm working on other fields, particularly the field of mixing, not only sprays, when I see a mixture. What do we see in this painting? We see a dispersing mixture that is a very tiny cloud, which is dispersing as it fades away in the diluting medium in the sky. And we see also a big fat storm cloud in which the fluctuations of concentration, let's say, are much more even than those characteristic of the tiny cloud on the left, which is extremely intermittent. And indeed, by looking at how in the laboratory, so back to the laboratory, no more in the, this picture is at the MFA in Boston. It is true that a mixture which is not allowed to interact with itself in a kind of confined manner evolves very differently than a mixture which, as it produces these stretched things we were seeing before, is enforced to interact with each other. So these lamella, which are produced by the flow, and this is a very simple flow in occurrence, these lamella, if you force them to interact with each other, to merge with each other, then they will produce a mixture which is, in its content, essentially different. This is something we know, this is something we have been documented in the laboratory, and this is something which was already contained in the painting by Signac. So yeah, relationship between art and science, in my opinion, and I like to have the feedback from the artist, the feedback from the scientist I know pretty much already, this is essentially a threefold relationship. First, science improves technology, offering new tools to artists. Obvious. We are happy to have fast cameras to document or observe the breaking of waves and reach a state of grace. Thermal cameras have been very interestingly used earlier this afternoon to make interesting movies of plumes, and artists are happy to have microscopes and all sorts of refined chemistry to make the restoration of masterpieces, the restoration of Saint-Anne by Da Vinci. So this connection is real, but it's obvious. I mean, we have been alluding to this. The connection and relationship between artists and science is not only that. This is a technological aspect of it, which is obvious, which is good, which is real, but there is not much to say about it. Second aspect, science describes natural objects, that's its goal, produces artifacts, such as man-made objects, and the laws ruling them. And we've been talking about breaking waves this morning. So I really would like to have the feeling of the feedback of the artists on that. Because I'm not sure that if I watch this picture, and if I know the nature of the singularity which has produced the breaking, this knowledge will alter in any way my perception, my sensation in front of this painting. In other words, having understood how natural objects have been built, what is the nature of the laws constructing the object itself, I'm not sure this is directly involved in what an artist wants to produce. Let me take another example. So this is one of the limits of the Savart sheets I was showing before. We call this a Savart bell because it looks like a bell. It has this clasp, this skirt, this fine structure. Is it really interesting to underline that there is a similarity in shape with the cucurbitacées we are used to in Provence? Yes, there is a similarity in shape. There is a, so what? This kind of Darcy Thompson approach, you probably know the famous book on Growth and Forms, the fact that there is an analogy, there is a correspondence in shapes, in forms. The fact that maybe this cucurbitacées can be understood in terms of the fundamental principles that explain the shape of the Savart bell. Is it interesting to the artist? I'm not sure. My personal conviction is that it's not interesting. Let me take the last example. We've been all along seeing these ligaments. Destabilization of these ligaments producing droplets. Is it really interesting? Is it really useful to underline the similarity in shape with the colonne sans fin of Brancusi? There is a similarity. There is a similarity. So what? Is it interesting to underline this? Even though there would be a connection between the laws having built the object on the left, the destabilization of the ligament, and the processes having served to construct the object on the right. Even though there would be a connection between the, there is no connection, strictly no, but even though there would be a connection, the knowledge of this connection, would it make this masterpiece of Brancusi a better masterpiece, or the experiment on ligament and droplet formation more scientifically sound? I'm not sure. In other words, this second aspect with which the relationship between science and arts is often confused may help really arts. And I will give an example. Science helps at discovering the mechanism of our perception. And I was talking at lunchtime with somebody who said, an artist, he's an artist, he said, we're thinking with our eyes. Did you say that? That's exactly that. We're thinking with our eyes. All right, so since science can help you to see and to understand what is really involved when you see, that might be useful to produce a new art. And I'm recalling here the famous history of the neo-impressionists, who first started their project from a scientific remark, and who were seeking information from science to produce a new form of artistic expression. So yes, having understood how our perception works might suggest new modes of expression. So you probably know that the neo-impressionists, well, starting in fact with Eugène Delacroix, who were, like anybody at the end of the 19th century, trying to change the form, trying to change not only the subjects, but the form. And I think the artists nowadays still are looking for new forms of expression. They said, okay, how do we really use color in our paintings? And they went and see Michel Eugène Chevreul, who was at the Tapisserie des Gobelins, so dyeing colors was something he was used to, and he had made a fundamental study of colors and the way colors look like when we see them. So this is Michel Eugène Chevreul, the same a few years after. Right? And as you all know, this is the famous chromatic cycle. He has devised the famous theory of the contraste simultané, underlying the complementarity of colors. What are two complementary colors? It's very easy to understand. For instance, orange is made of a mixture of yellow and red. Its complementary color is the only primary color which has not been used in the mixture process. So it's the opposite on the chromatic circle. This is the blue. This, together with the subtractive synthesis, has allowed them, and this is again something by Paul Signac, to devise a new way of expression, the famous pointillism, neo-impressionism, science of division. And as you can see, this process of simultaneous contrast is widely used in this exercise of style on the famous portrait of Felix Fénéon. All right, they have been criticized for that. The criticism was that the neo-impressionists are too much scientists, and this prevents them from express their sensations at freedom. And the criticism is, I think, in general, correct. However, this criticism, according to Paul Signac, does not apply to neo-impressionists. So they use science to enhance their inspiration. I'm translating. They use it to service what they want. And I think this real story of the neo-impressionists is a real achievement of the use of science, the correct use of science in order to improve art, that is to make a new art and a new form of expression. All right, so will the knowledge of fragmentation phenomena renew art in any way? Not sure. But that's not a big deal, because I think that artists have, in some sense, always been ahead. When Neil Armstrong landed to the moon, he saw the footsteps of Jules Verne, Steve Weinberg. And as a matter of fact, talking about clouds and water, we knew already that there is a wealth of interesting thing there and a very interesting life. Has somebody recognized? Very good. And with the original song. All right.